seeing isomerism. Isomerism is the phenomenon in which, say, compounds exist with the same molecular formula but different arrangements of atoms and different properties. Such compounds are called isomers. The compounds with the same molecular formula but different arrangements of atoms and different properties are called isomers. Isomerism can be broadly classified into two types: structural isomerism and stereoisomerism. As you know, structural isomerism is due to the difference in the structures of the molecules. The structural isomers will have different structures, while stereoisomerism is due to the difference in the spatial arrangements of the atoms. We have to consider the locations of the atoms present in space. That's about the stereoisomerism. Then the structural isomerism can be classified into four types mainly. One is called, we have seen already, that's the chain isomerism or nuclear isomerism or skeletal isomerism. Second one is functional group isomerism or functional isomerism. Third one, that is position isomerism, we have to see it today, and metamerism. Stereoisomerism can be classified again into mainly two types. One is called the geometrical isomerism and the other is called the optical isomerism. Let us go to the chain isomerism. Say in the chain isomerism, the isomers have different carbon skeletons, different carbon chains, different carbon nuclei. There will be a difference in the carbon skeletons of the isomers. That is a chain isomerism. Then functional group isomerism or functional isomerism. Here isomers have different functional groups. The functional groups of the isomers will be different. Now let us go to the third type, that is the position isomerism. Let us say isomerism. In the position isomerism, the functional groups will be the different. So the third one, that is position isomerism and the position isomers. Here, the isomers have same functional group. They have same functional group. The isomers have same functional group, but the positions of the functional group will be different. The positions of functional groups will be different. The positions will be different. Same functional group, but the positions of the functional groups will be different. Different positions for the same will be different. See here, the positions will be different. Will be different. Different positions. Okay. Let us see one example. Say propane 1 mole and propane 2 mole. Two alcohols. One is, say, CH3, CH2, CH2OH. CH2, CH2OH. The molecular formula will be C3H7O. OH. C3, S7OH. You take another compound, CH3, CHOH, and CH3. same molecular formula, same functional group also. So same molecular formula, same functional groups, but the positions of the functional groups will be different. You give the number of the carbon atom 1, 2, 3. Similarly, 1, 2, 3. So the positions of the OH groups are different. Same molecular formula, same functional group, but the different positions for the functional groups. Compound 1, that is called 1-propanol or propanol 1 or propan 1-ol. Propan 1-ol. More details we can see later. How does the name come? We can see it later, IUPAC rule. So this propan 1-ol or 1-propanol or propanol 1. And second compound is propan 2-ol. Propan 2-ol. See, both these compounds are propanols. Propanols. So just forget about the position, then the compound will be propanol. Propanol. Both are propanols. But the positions of the ol. Ol means OH group. The positions of the OH group will be different. So, position isomers have same molecular formula, same functional group, but the positions of the functional groups will be different. For example, propan 1-ol and propan 2-ol, two position isomers. Similarly, say we can have another compound, say CH3, CH2, CH2, say for example Cl, then CH3, CHCl, and CH3. Here also, you can number the carbon atoms. Say 1, 2, 3. 1, 2, 3. The functional groups, same. Chlorine, both are halogens, both are chlorines, chloroderivatives. The first compound is called 1-chloropropane. 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 And the second compound is 2-chloropropane. 2-chloropropane. See, both the compounds are chloropropanes. Both are chloropropanes. But the positions of the heteroatom, that is the chlorine atom, say that is different. One is 1-chloro and the other is 2-chloro. The positions are different. So such isomers in which the functional groups are the same, but the positions are different. And that's called the position isomerism. Now I come to the fourth one. That is called the metamerism. Metamerism. Metamerism is seen in the compounds like ethers, say ethers, compounds like ethers, then secondary amines, then ketones. So we can see metamerism in ethers, secondary amines, and ketones. Such isomers are called metamers. Metamers. The isomers are called metamers. So metamerism and the metamers. That is due to the difference in the alkyl groups or aryl groups attached to same functional group. So it is due to the difference in the difference in the alkyl groups. The alkyl groups are different. The difference in the alkyl groups attached to same functional group. Attached to same functional group. So same functional group, but to the functional group, the alkyl groups attached are different. Alkyl groups means methyl group, ethyl group, propyl group, etc. Such groups are called alkyl groups. All these groups are coming from alkanes. We can see that when we deal with alkanes, hydrocarbons. So methane CH4, from that we get a methyl group, CH3. Ethane, C2, C2H6, and one hydrogen is removed, C2H5, ethyl group. So such groups are called the alkyl groups. So metamerism or metamers, that's due to the difference in the alkyl groups attached to same functional group. So they have same functional group, same molecular formula, but the alkyl groups will be different. To the same functional group, we are attaching different alkyl groups, and it is seen in ethers, secondary amines, and the ketones. So, what are ethers? Do you remember? We had seen last day. So, we have a compound like this, an oxygen bridge. Say, an oxygen bridge between two carbon atoms. There is an oxygen bridge between two carbon atoms. Such compounds are called ethers. We have to study that in the second year, ethers. So, in the ethers, there is the ether linkage known as the oxide linkage. There is the oxide linkage. That oxide linkage is between two carbon atoms. There is oxygen atom. So here, wait. Say here, no, other bonds. Oxygen valence is equal to 2 only. Oxygen valence is equal to 2 only. So there is an oxide linkage between two carbon atoms. And such compounds are called ethers. And what are secondary amines? Secondary amines have, they have the structure like this. Say there is a NH group, NH, and such compounds are called secondary amines. So in secondary amines, there will be NH group. The functional group is NH group. That is a secondary amine. And on both sides of the NH group, there will be different alkyl groups. And you take, say, ketones. Ketones will be having the functional group C double bond O group. And such compounds are called ketones. C double bond O group. So here the functional group is a CO group. It is called the ketonic group or carbonyl group. And in these three types of compounds, the alkyl groups attached to both sides of the same functional group will be different. That is in the metamerism or metamers. So metamers have same molecular formula, same functional group. But the alkyl groups attached to the functional group will be different. And it is seen in ethers, secondary amines, and ketones. So in ethers, there is an oxide linkage between two carbon atoms. And that linkage is called the ether linkage. So we can write either as COC, and that is the linkage in the ethers. On to the secondary amines. In the secondary amines, the functional group is NH. More details, second year we have to study. You just keep it as such. So, to the NH group, secondary amino group, the alkyl groups attached will be different. And ketones, there is a CO group. The functional groups attached will be different. Let us take some examples for, say, ethers, amines, and ketones. Ethers, amines, and ketones. Say, for example, you take a CH3O, CH2, CH2, CH3, CH3. Say, an ether like this. There is the ether linkage. Here there is the ether linkage. So this compound is an ether linkage. You take another ether, CH3, CH2, O, CH2, CH3. Say the alkyl groups attached to the ether linkage are different. Say in the first compound, there is a CH3 group and CH2, CH2, CH3 group. The two alkyl groups are different. See here, this is the alkyl group and the methyl group. Here the alkyl groups are this. So the alkyl groups attached are different. You just take the molecular formula, can say that the molecular formula will be the same. Both these compounds, both these ethers are the same molecular formula. You come to secondary amines. Say, for example, say NH, CH3, CH2, CH2, CH3. A secondary amine. Here there is the secondary amino group. Similarly, CH3, CH2, NH, CH2, CH3. Here the functional group is the same, but the alkyl groups attached are different. Say in the first compound, CH3 group and CH2, CH2, CH3 group. In the second compound, there is ethyl and ethyl. Two ethyl groups are there. The alkyl groups. These groups are called the alkyl groups. These are the alkyl groups. So here, the alkyl groups are different in this secondary amine also. Similarly, you can see in ketones. In ketones also, there will be different alkyl groups attached. So, for example, CH3, C double bond O, CH2, CH2, CH3. You take another ketone, CH3, CH2, C double bond O, CH2, CH3. I am taking only simple examples. Only simple examples are taken. There is the ketonic group. Here also there is the ketonic group. So same molecular formula. You check the molecular formula. Can say that the molecular formula will be the same. So same molecular formula, same functional group also. But the alkyl groups attached, the alkyl groups, they are different. And this type of isomerism is called a metamerism. And such isomers are called metamers. So much about the structural isomerism. So the structures of all these isomers are different. Okay. Now let us go to the second type, that is a stereoisomerism. Stereoisomerism. And the isomers are called stereoisomers. And that is due to the different spatial arrangements. The different spatial the different spatial arrangements of atoms. The different spatial arrangements of atoms. So the direction of the bonds must be considered. The positions of the atoms in space. The positions of the atoms in space, that must be considered. Not simply the structures. By structure we mean, say, the different types of bonds. So the bonds are between the carbon atoms, or carbon and oxygen, or carbon and hydrogen, and that's about the structure. But in the spatial arrangement, the spatial arrangement is called a configuration. That is called the configuration. configuration of the molecule. That is called the spatial arrangement. So in that case, we have to consider the positions of the atoms in space, exact positions, so that we have to consider the directions of the covalent bonds. We have to consider the directions, the bond angle, all these things must be considered. And due to the difference in the spatial arrangements of the atoms or configurations, stereoisomerism arises. And such as isomers are called stereoisomers. We have seen stereoisomerism can be classified into two types. One is called geometrical isomerism, and the second one is called optical isomerism. Let us say two types. One is called the geometrical isomerism. Geometrical isomerism. The other is called optical isomerism. Optical isomerism. Let us explain geometrical isomerism and optical isomerism. So let us now go to the geometrical isomerism under the heading stereoisomerism. Okay. So let me take first geometrical isomerism. Geometrical isomerism. It is also called Cis isomerism. Cis isomerism. Geometrical isomerism or cis isomerism. This isomerism is seen in the alkene derivatives. These are seen in alkene compounds, alkenes. You know, in alkenes, there will be carbon-carbon double bond. There will be carbon-carbon double bond. And so, geometrical isomerism is seen in the compounds which are having carbon-carbon double bonds or alkenes. So, alkene-like compounds can show cis isomerism or geometrical isomerism. Let us take say some examples for this. You take a compound like this, C double bond C, and here we have two more valences attached to this. Suppose there is a CH3 group here, and here there is H. And here CH3 group, and here there is H. Okay, it's a planar molecule. Double bond, so this is a planar molecule. So we have a compound like this. So what is the structure? CH3, CH, double bond CH, CH3. And this is the structure. That means in the structure, the various bonds are shown. Only the various bonds. That means carbon atom number 1. That is having 3 hydrogen atoms, and it is attached to one more carbon atom. Second carbon, there is only 1 hydrogen atom, and it is attached to 2 other carbon atoms. So only the structures are mentioned in this, and this is called a structural formula. But say what I have drawn here, it shows the actual location of the various groups and atoms. It's a planar molecule. And in this planar molecule, what will be the locations of say the groups? You take a CH3 group, here also CH3 group. Similarly, you can take a H and H. See here, the similar atoms, hydrogen, here hydrogen. So similar atoms or similar groups are on the same side of the double bond. So similar atoms or groups on the same side of the double bond. Same side of the double bond. Carbon-carbon, double bond, same side. You consider a plane like this. Say, a plane perpendicular to the board, passing through both the carbon atoms. Say, a plane like this. Can you say? Say, you consider a plane like this. A plane perpendicular to the board. A plane perpendicular to the board. And it is passing through both the carbon atoms. Do you get me? Consider a plane perpendicular to the board. No, the molecule CHCS3 double bond CHCS3. That molecule is a planar molecule. All the atoms or groups are lying on the same plane. That means the plane of the board. They are on the same side, on the same plane. Same plane. The CH3, and hydrogen. All these are the same plane, that is plane of the board. Now you consider, we have two carbon atoms, carbon atom 1, carbon atom 2. So you have two carbon atoms, 1, 2, and the hydrogen, CH3. All these are in the same plane. Now you consider a plane perpendicular to the plane of the molecule. Suppose, say this is the plane of the molecule. All these are in this plane. It's plane. Carbon atom 1 here, carbon atom 2 here, then CH3, H. All are in the same plane, on the same plane. Now you consider a plane perpendicular to the plane of the molecule. See like this, a plane. And this plane is passing through both these carbon atoms. The plane passing through both the carbon atoms. You consider such a plane. Now you come to this again. Okay, let us see. Let us go back to the structure. So consider a plane perpendicular to the board. Perpendicular to the board. And the plane is passing through both the carbon atoms. Say a plane like this. Plane perpendicular to the board, passing through both the carbon atoms. Now you can see that the CH3 groups are on the right side. See, according to me, say both the CH3 groups, similar groups, are on the right-hand side of the plane considered, while the hydrogen atoms are on the left-hand side of the plane. So similar atoms or groups are on the same side of the double bond. Remember, you consider a plane perpendicular to the plane of the board. All these are lying on the same plane. All these are lying on the plane of the board. Remember that first. Hydrogen, carbon, CH3. All these groups are lying on this plane of the board because carbon atom, the carbon atom, C double bond, C carbon atom, the doubly bonded carbon atom has a sp2 hybridization. It has a sp2 hybridization. So it is planar. You have studied hybridization. It is planar. So this molecule is planar. This molecule as a whole is planar. And all these atoms and groups are lying on the same plane. That means the plane of the board. Now you consider a plane perpendicular to the board. Not only that, the plane is passing through both the carbon atoms. Now you examine the positions, the stereo arrangement, the spatial arrangement of a similar atoms and groups. Can say that similar atoms, hydrogen, same side, left-hand side of the double bond. Similarly, similar groups, CH3, on the same side of the right-hand side here. Right-hand side to me now. On the right-hand side of the double bond. So, similar atoms or groups are on the same side of the double bond. If it is so, it is called the Cis Isomer. It is called the Cis Isomer. Cis Isomer. under this compound, cis isomer, the same, cis means the same. The meaning is this. The meaning of a cis. Cis means same, same. What is same here? Similar atoms or groups. Similar atoms or groups are on the same side of the double bond. And so that isomer is called the cis isomer. You consider another isomer, say like this, C double bond C. Here there are two more bonds. Now you change the positions. Say here CH3 and here there is H. Okay. Now you change the position. You just interchange this. Interchange this. Then you will get the first you interchange. First you interchange the positions. So you get the CH3 on the left hand side and hydrogen on the right hand side. And the other one you keep it as such. So this H and the CH3. Now you consider similar atoms and groups. Say similar groups, CH3 groups. Similarly, you consider similar atoms. Say CH3, H and H, similar atoms. Can see that here the similar atoms and groups, similar atoms or groups are on opposite side of the double bond. Opposite side of the double bond. You consider a plane as before. As before, you consider a plane perpendicular to this board. A plane perpendicular to this board. And the plane is passing through both the carbon atoms. A plane passing through both the carbon atoms perpendicular to the board. And we examine the positions of similar atoms and groups. You can see that similar atoms and groups are on the opposite sides. Say CH3 left hand side here CH3 on the right hand side. Similarly, here H on the left hand side, here H on the right hand side, opposite sides. And such isomer, that is called a trans isomer. It is called a trans isomer. Trans isomer. And this compound, trans means opposite. Trans means opposite. And what is opposite? Similar atoms or groups are on the opposite sides of the double bond. Similar atoms or groups are on the opposite sides of the double bond. Then it is called the trans isomer. You can see that both these compounds are having the same molecular formula. They have the same structure, bonding nature. See here, same structure, same bonds, but the positions of the bonds are different. The positions of similar atoms or groups are different. The spatial arrangements of similar atoms or groups are different. If similar atoms or groups are on the same side of the double bond, then it is called the cis isomer. And if the similar atoms or groups are on the opposite sides of the double bond, then it is called the trans isomer. And this type of isomerism, that's called the geometrical isomerism or cis trans isomerism. The geometries will be different. The geometries of the molecules are different. So, in geometrical isomerism or a cis trans isomerism, the similar atoms or groups may be on the same side or on the opposite sides of the double bond. If the same atoms or groups are on the same side of the double bond, same side of the double bond. See, the side, say like this. You consider a plane like this. Similarly here also, you consider a plane like this. Now you can see that in the cis isomer, the CH3 groups are on the right hand side. and hydrogen atoms are on the left-hand side in the cis isomer. But in the trans isomer, in the plain bond, similar groups, CSP groups, are on opposite sides. In the first carbon, doubly bonded carbon atoms, the CSP groups are on opposite sides. Similarly, hydrogen atoms are also on the opposite sides. It's called a trans isomer, and this type of isomerism is called a cis trans isomerism. Okay. And this is due to the geometrical isomerism is due to the restricted rotation about the carbon-carbon double bond. If say carbon-carbon double bond is formed, the molecule cannot freely rotate about the carbon-carbon bond. The molecule cannot rotate freely about the carbon-carbon bond. The rotation is restricted. So, geometrical isomerism is due to the restricted rotation about carbon-carbon double bond. There is no free rotation. Free rotation is restricted. Free rotation of the molecule about the carbon-carbon double bond. The rotation of the molecule about the carbon-carbon double bond, that is restricted. It cannot freely rotate. If once the cis form is formed, it is stable. If once the trans form is formed, it is stable. Okay. So geometrical isomerism or a cis trans isomerism is due to the restricted rotation about the carbon-carbon double bond. The free rotation is blocked. Free rotation of the molecule about the carbon-carbon double bond, that is not allowed. So once cis form is formed, it is stable normally. If a trans form is formed, it is stable normally. And it can be changed when it is heated strongly, then the pi bond will be broken. You know, the carbon-carbon double bond, both the bonds are not identical. One is a sigma bond, the pi bond is the other one is a pi bond. Pi bond is weaker. So when it is heated, say the pi bond will be broken. When pi bond is broken, then what is remaining there is only carbon-carbon single bond. Only carbon-carbon single bond. Then free rotation is allowed. So the cis form can be converted into the trans form, or the trans form can be converted into the cis form. So if there is carbon-carbon single bond only, there is free rotation. The molecule can freely rotate about the carbon-carbon single bond. But if there is carbon-carbon double bond, the free rotation is not allowed. It is restricted. So if once a cis form is formed, it is stable. If once a trans form is formed, it is stable. Okay. So you have to remember 2 points here. One, geometrical isomerism or a cis trans isomerism, or geometrical isomers or a cis trans isomers. What is the definition? In the geometrical or a cis trans isomerism or geometrical or a cis trans isomers, the similar atoms or groups, isomers, I told, the similar atoms or groups will be on the same side of the double bond or on the opposite side of the double bond. If similar atoms or groups are on the same side of the double bond, then that isomer is called a cis isomer. And if similar atoms or groups are on the opposite sides of the double bond, 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 double bond. Very careful, double bond, not a single bond. If single bond, the free rotation is there. If double bond, no, there is no free rotation. So that is why I give emphasis to double bond, carbon-carbon double bond. So if a same or similar atoms or groups on same side, the double bond, cis isomer. Opposite sides, then it's a trans isomer. And it is due to the restriction of free rotation about the carbon-carbon double bond. Okay. Now, you just try to remember the name of the compound given. The cis isomer, both are the same, both are having the same molecular formula, same functional group, same groups and all these things. The first compound is called butane, that is 1,2. So butane, the name of the first compound. The name of the first compound. You can write it, say, you can write the name of the compound, write the name of the compound below this. Below this, you can write the name. We'll study that later. The first compound is called cis form. So it is called, say, cis. Both sides are same atoms and groups. So cis, then but, 4 carbon atoms. 1, 2, 3, 4. 1, 2, 3, 4. 1, 2, 3, 4. 4 carbon atoms. So cis butene, 2-ene, and the other one is trans 2 or 2-butene or but2-ene. You can write say different ways, say like this. So trans but2-ene, trans but2-ene. The compound can be named as but2-ene or 2-butene or butene 2. but2-ene or 2-butene or butene 2. The first one is cis, so it is cis 2-butene, and the other one is trans 2-butene. Or you can write it as cis 2-butene and trans 2-butene. Or you can write cis butene 2 and trans butene 2. All these names are allowed by UPSC. Don't fear about the naming. You will not fear anything that I know, that I agree, but the details we'll study in the coming chapters. How to name the alkenes, we'll study that. Okay. So that's about the geometrical isomerism. And what is left in isomerism? What is left? That is only Achut. What is left in the optical isomerism? That we will see in the next period. It will take 1 hour to explain. Remember all these isomerisms, especially geometrical and optical. It's very important. That is very necessary for the second year. Very necessary. It is very essential for the second year. So you have to remember all these things more. So we can see the optical isomerism in the next period. Let me stop now. Thank you.